Buenas tardes, me llamo Brian Day y trabajo en NASA en el Instituto Virtual de Investigación y Exploración del Sistema Solar. Hoy vamos a escuchar una presentación muy interesante de uno de nuestros investigadores. Jim Head es un profesor y científico con nuestro equipo de la Universidad de Brown. Su estudio de la Luna incluye haber participado en las misiones Apolo a la Luna. Hoy va a hablar con nosotros.
English is very poor, so I hope you can understand my English. So I teach planetary geology here at Brown University, and I'm very excited to have been involved in the NASA space exploration program since the Apollo days, since we sent humans to the moon and returned them safely, and they undertook extensive exploration. So today we want to talk about climate history of Mars and indeed think about future robotic and human exploration. So you all know what weather is. Weather is a changing, it's hot one day, it's cooler the next, it rains one day, it doesn't rain the next. That's the short term. Over short time periods, the changes we see in weeks to months and our lifetimes are typically related to weather. But over longer periods of time, hundreds of years, thousands of years, these changes map out into broader scale changes, which are known as climate, the climate variations. And so that's what we want to study for Mars, because Mars is an incredibly interesting planet. We want to understand climate change for the Earth, but we also want to understand it for Mars, and then compare the two to help us understand very fundamental things like, when did life start on the Earth? What were the conditions under which life began? And very important concepts like this. Now, many of you may not think much about life on Mars. Next slide, please. But indeed, when we do look at Mars, we see evidence. Next slide, please. We do see evidence from the meteorites that are brought from Mars by large impacts. They're actually excavated from the surface of Mars. An impact hits Mars, the ejecta comes out, and then it's transported to the Earth. We see evidence for things that could be evidence for small particular features that might indicate life. So we're very interested. Was life on Mars in its early history? Could life have evolved on Mars? And since these rocks can be blasted off Mars and brought to Earth, maybe we might be Martians. Think about that. Rocks that, if life started on Mars and a rock was thrown off Mars and fell on the early Earth, maybe it brought life to the Earth. So instead of thinking about, are there Martians, maybe we're Martians. It's something to think about. So if we take a look then at the characteristics of the surface of Mars, we can study the climate history. Next slide, please. Now, Mars is not like the Earth in terms of its climate. It's very different, and there's a lot of very interesting reasons for this. For example, on the Earth, we have very active weathering. We see a lot of erosion from the water interacting with the rocks, rivers and streams and so on. And we also have plate tectonics. In the upper right-hand image, you can see the ocean floor, and this very distinctive pattern is testimony to the plates moving around and interacting. This doesn't happen on Mars. Mars is very stable. The third thing is that we have huge oceans. The upper image on the left, you can see the beautiful oceans on the surface of the Earth, 2/3 of the surface of the Earth. That's a huge amount of water, and it also helps to interact with the atmosphere and damp out many of the kinds of changes that we might see. And then, of course, when you have the heat of the sun heating up the atmosphere, you also have that same hot air heating up the ground. So there's absolute coupling between the solar insolation, the solar radiation, the atmosphere, and the surface. And this is very different than what we see on Mars. If you look at Mars in the lower image and on the left, Mars is very, very slow weathering, much, much slower than on the Earth. It has no plate tectonics. The topography we see in the lower image in the middle is very similar to what it was billions of years ago. And indeed, we don't have any oceans on the surface of Mars at the present time. We think there may have been some in the past, but that's something we can explore to try to find out. And then, of course, the atmosphere and the surface coupling are extremely different as well. The atmosphere of Mars is so thin, it's about 1/100th that of the Earth, that there is not very much atmospheric coupling. Next slide, please. So how do we learn about the climate of Mars? How can we study Mars? It's very far away. It's hard to get to. It's hard to observe. How do we study it? Well, the first thing is, ever since we first went to Mars 50 years ago, we've been watching Mars and studying its atmosphere. So the image in the upper left of the surface of Mars shows you all these different things we can see: water ice clouds, polar deposits, dust storms, polar caps, and it also shows you that we have things like a Viking lander, 1976. Many, many years ago, these landers landed on the surface and in fact provided weather stations, and each of these missions provides weather stations on the Earth. So we've been looking at Mars for 50 years, and that's beginning to get the transition between weather and climate. So we're on the right track because we can study how Mars weather works and map that into how climate works. We know that Mars' atmosphere is made of carbon dioxide, the vast majority of carbon dioxide, which is very, very different than the Earth's, which is nitrogen and oxygen. We also know that it's very cold and very dry on Mars at the present day. Next, please. So when we think about the geological history of Mars, we can divide the history of Mars up into 3 major periods. And these are quite interesting because we can actually see all the geological history on the surface over the course of 4.5 billion years. On the Earth, it's been modified, it's been pushed back down into the interior, and so we have not had much chance to really see it in detail. And so it's very hard for us to know the first 2/3 of Earth history. But we can see it on Mars, so we learn what was going on in those early periods of history. So the Mars history can be divided into 3 periods. On the right, the Amazonian, shown in yellow, is about 3 billion years long, and that was a time when there were very low rates of impact craters forming, and it's a cold and dry Mars. Now in a minute we'll see that we go to Antarctica, very cold, very dry place, the Antarctic dry valleys, to study the geological processes, because in Antarctica it's very much like being on Mars every day. It's great fun. We camp out for 2 to 3 months with no heat except for a little stove, and we experience what it's like being on Mars. And that's what Mars has been like for the last several billion years. So Amazonian, there's a little bit of volcanism, big polar caps, but not much else is going on. If we go to the middle period, the Hesperian, that was from about 3 billion to about 3.7 billion years ago, shown in blue. And that's where we see huge channels coming out from the surface. This is the Tharsis area, and from around the edges we see lots of water flowing out into the northern lowlands. This is the northern lowlands here. The blue is a depression. This, in fact, is something where we see potential evidence for water accumulating there to form an ocean. In the first period, the Noachian, from about 3.7 billion years ago to 4.5 billion years ago, this was a time which we think we see evidence for a warm and wet early Mars. Many people say, you'll visit the NASA websites, they'll say scientists think that in earliest history of Mars, in the Noachian, it was warm and wet, much more like the climate you're experiencing in Mexico City today and that we experience over a significant part of the Earth. So was Mars warm and wet early on? There's lots of evidence for that. We see lots of stream channels, but there's no water in them now. We see lots of lakes where water flowed in, the streams go in, the streams come out. They had to be filled with water. Lots of evidence for running water on the surface, which makes a lot of scientists conclude that it was a warm and wet period. So how do we go back through this geological history to try to find out what was going on with the climate? Next slide, please. So one of the things that we can study here is looking at the ways in which climate changes. Okay, so these are known as the astronomical climate forcing values. This is something that describes a set of very straightforward things. If I take this globe and pretend that you are the sun, okay, then right now at the polar cap where all the ice is, not very much solar energy is hitting the surface. It's mostly at the equator. But if the axis changes and points towards the sun, it's going to heat up that ice and place it into other areas of the planet. At the same time, if it's a circular orbit around the sun, the same average amount of solar energy hits the surface, but if that becomes more oblique, more eccentric, if you will, then sometimes Mars can get much closer to the sun than at other times. So these are the kind of things that can really cause fundamental differences in climate change. And the biggest one is the obliquity, that is to say, the tilt of the axis, because it controls where the sun hits the surface. So that's another thing we can do. And then another thing we've learned is to use computers to make very complex models of the atmosphere. This is well known. This is how weather predictions are made on the Earth. This is also how weather predictions and climate studies are done, by putting it into a big computer model, making predictions, and then seeing what comes out. So we have that as well. And the next slide. We can also study the characteristics of what we call non-polar ice. Next slide, please. If we think about the distribution of ice around the poles, so in this diagram here, we're looking at a map, a flattened out map of the surface of Mars, and at the top and the bottom of that map, we would expect to have, indeed, as we see today, the polar deposits. But if we change the obliquity of Mars, then it's quite possible that that ice will be mobilized and redeposited elsewhere as glaciers or maybe other things. So this map shows you the distribution in these numbered little labels here, the distribution of places where we see non-polar ice, that is to say, ice deposits and glacier deposits that are not at the poles like they are today. This is evidence for differences in the climate history of Mars. If we see evidence for glaciers in the equator region, wow, that says something's really different in the past history of Mars than it is today. So we can use this set of geological records to go back and look at the climate change. Next, please. Now, I mentioned, too, that we go to Antarctica. This is really a great adventure, if you will. It's cold. You have to really like the cold. It's almost always below zero. The mean annual temperature is like minus 20 to 30 degrees centigrade. Maybe for a day or a few hours a day, it might get above freezing in southern summertime, but generally it's extremely cold. And so you have to really like the cold, but when you get there, it's an amazing thing to see. So these are some panoramas, if you will, some views of what it's like. And it doesn't look like Mexico City. It doesn't look like my home, Providence, Rhode Island. It's very, very different. There are no plants, there are no animals, there are rocks, and there's ice. And so we can study this to look and see what Mars is really like. And the similarities are completely amazing. Next slide, please. If you take a look at this lower left and lower right pictures, you can see evidence for rocks on the surface of Antarctica and rocks on the surface of Mars. And indeed, they're very similar. So we can study these and learn how these processes work on Mars. That's me in the middle picture there, and you can see that there's frost all around my coat and the hat, and you can see icicles on my mustache from the really, really extreme cold, and breathing very hard as you're walking up these glaciers and these hills and so on. So it's a great adventure to be able to go there and study how Mars works by being on the Earth in the most Mars-like environment on the Earth. Next, please. Another thing we have is mineralogical data. So if you think about how rocks and water interact, if you have rocks and water interact a lot, it will break the rock down and it will make it into a clay. That is to say, you'll see it break down, you'll see the minerals change, and they go from very distinctive igneous minerals to minerals that are much more subject to weathering and caused by weathering, like clays, for example. Because we have remote sensing data in orbit, that is to say, remote sensing instruments in orbit, we can also look at the mineralogy of the surface. And two pioneering scientists, Jean-Pierre Bibbering in France, and a professor here at Brown, Jack Mustard, and a former student here at Brown, Scott Murchie, were really instrumental in flying a spectrometer instrument which can provide us with information on the mineralogy of the surface of Mars. And it's just amazing what you see in the three colors in the bar at the bottom are differences in the basic mineralogy that tell us that the Amazonian, in the kind of like salmon bar, colored bar, that was a period of almost no alteration at all. It looks very much like Antarctica. In the Hesperian, the green bar, those are sulfates. Something unusual was going on there. Probably a lot of volcanic activity. And in the purple bar, in the Noachian, the bar is related to clay minerals. So that says that a lot of erosion, a lot of weathering was going on, which is consistent with a warm and wet early Mars. Next, please. So our strategy then is to take this new information and use the geological column here, and then start at the Amazonian, where we are today, and go back in time until something says in the geology something is very, very different. So let's go on this adventure. Let's start with today, what we know today from all the missions we have in orbit right now, and go back in time to try to understand the climate history of Mars. Next, please. So scientists like myself and my colleagues pose a lot of questions. And so we try to go in and answer them. So for the Amazonian, the yellow period, we ask things like, do we know what the climate history in the last 20 million years is like? Something very close to what we know today. So we look at the most recent deposits, and then we ask the question, what about the last 3 billion years? What about the rest of it? Has it changed radically from what we see today? And that's a really good question. So let's go back and try to figure that out. In the next slide, you can see one of the most recent deposits on this map. So in the red arrows, from about 30 degrees north and south latitude to the poles, we can actually see a deposit called a latitude-dependent mantle. This is really interesting because this is superposed and overlain on most of the other deposits. And in the next slide, you can see what we think was going on. There's a geological map in the upper left. The little boxes show the kinds of terrain we see. And in the lower left, we see evidence for the way in which the obliquity of Mars varied as a function of time. Notice in that last diagram, notice that the gray area has a lot of wiggles in it that go up and down a lot, okay? On the left-hand side is where we are today, and the wiggles aren't going up and down a lot. This means that the obliquity is now stable at 20 degrees, etc. And in the past few millions of years, the obliquity was going up and down a lot. We think that on the basis of this reconstruction and this prediction, that Mars looked like the upper right-hand picture, that it was in an ice age, that there was ice deposited when the obliquity was high at all the way down to 30 degrees north and south latitude. So this would predict then that Mars was in an ice age not too long ago, and that in fact climate change was happening. So Mars is currently very cold, but back then it was even more distinctly ice-like because the ice was redeposited from the poles into these low-lying areas. Next, please. Now, we also see evidence for glacial-like deposits in the 30 to 50 degrees north latitude, and they're much more extensive. Shown on the left is one of those types of deposits, and shown on the right is another. They're called lobate debris aprons and lineated valley fill. And so we've done some climate modeling to see how you could put ice there and how long it would stay there and what kind of flow patterns you would get. And in the next slide, you can see exactly the kind of predictions that are made and what we see. So in fact, at 30 degrees north latitude, on the left, we see the kinds of features we see that look exactly like, on the right, glaciers that we see on the Earth today. So in the right-hand side, these are glaciers in the mountains. It could be in the mountains of Mexico, could be in the mountains of Switzerland. But the point here is that on the left, it's on Mars, and they're exactly the same kind of features. And this indicates that a lot of ice was accumulating here. And by looking at the climate models, this means that the average obliquity, the change in the axis of the planet's rotation axis, was in fact of the order of 35 degrees. So that's amazing. So we're seeing climate change going back and forth as we go back in the past history. These deposits were in place about 200 million years ago. Next, please. Well, furthermore, if we look at this map again, we see actual evidence for tropical mountain glaciers. Now that seems like a complete contradiction. How can you have glaciers in the tropics where it's so hot? That's because temperature varies as a function of altitude. So if you get way high, you can actually accumulate ice and create glaciers. For example, in Africa, Mount Kilimanjaro has glaciers on the top, yet it's right on the equator. So we see evidence in these yellow deposits in the middle image and in these images in the lower left and lower right for tropical mountain glaciers, and they're huge. How do these form? We work with the climate modelers. The next slide, please. And the climate modelers were able to show us that when the axis is tilted 45 degrees, as you can see in the image in the middle, that the polar water comes down towards the equator, goes up the side of the Tharsis, hits the side of the mountains, and then it snows out, as you can see in this diagram here. So at 45 degrees, we expect to have tropical mountain glaciers. This is really amazing. So we see a lot of success in understanding climate and its change throughout the Amazonian. Next slide, please. So on the basis of our study, then, we can conclude that for that 3 billion years period of history, it was an extremely cold, extremely dry climate throughout about 2/3 of the history of Mars. The climate is really related to changes in the spin axis parameters, and the current obliquity, what we see on Mars today, could be really anomalous. Mars, as we see it today, may not be Mars in its typical conditions. So let's go further back in time. Next slide, please. And see what we can find out from earlier history, such as in the Hesperian, circled in, if you will, put a box in red. That's from about 2.9 to 3.7 billion years ago. And this is a period of time in which we have some amazing things going on Mars. You know, we don't see evidence in the Amazonian for rainfall because it's too cold. There's not enough water in the atmosphere, and it's too cold to actually have rain. We might have a little snow from time to time, but even that's pretty minimal. So what happens back here? What we observe is huge, huge rivers that have no water in them anymore. And they're not rivers that came from rainfall, torrential rainfall, like a tornado or a monsoon. They came out of the ground. So for some reason, around this Tharsis region of Mars that we see here, the ground cracked from a lot of cracking associated with the volcanism, and water poured out to create huge flash floods onto the surface. So in the next slide, you can see, go two forward, and the next one, please. You can see evidence for this in these images, particularly in the upper left and the middle left. You can see evidence for water that flowed out over the surface. The blue in the geological map in the background is related to the flowing water that flowed out billions of years ago, and it really eroded the surface. In the upper left-hand image and in the central image, you can see evidence for rivers having been carved hundreds of kilometers across, completely carving the landscape. So that's a lot of water coming out of the interior of Mars, the near subsurface, as a function of time. This is really amazing. I mean, it's something we've never seen on the Earth. And so if we go to the next slide, we can ask the question, where is all that water going to go? And so now you're in the lower set of maps, you're taking this and turning it to the North Pole so you can see what the low depressions look like. And it looks like, from the basis of our mapping, that any water that flowed out into the surface of Mars would flow down into the northern lowlands and fill it up, as you can see in the black image there, with water. So it's quite possible Mars had huge lakes, possibly even oceans, in the Hesperian part of Mars history. So this is amazing. This is very different. This is not what we see today. It's not what we see in Antarctica. And it's not what we would expect over the last 3 billion years. So something really radically different indeed changed. Next slide, please. So the Hesperian, then, is a very unusual period. And in fact, the other thing you see during the Hesperian is lots of volcanic activity. And we think that may have something to do with the presence of sulfates in the mineralogy. Next, please. But what about the Noachian? Now we're back to the time where we think we see lots of evidence. We do see lots of evidence for flowing water. We see lots of evidence for clays, as you can see in that blue box in the bottom. And so this seems to be the period of time when it's most likely to be warm and wet. This is really exciting because now we're at the place where Mars in the past history might be like it is today. So what kind of evidence do we see that gives us an idea? First of all, we want to ask a lot of questions about the Noachian, like scientists do, to try to understand what's going on. Next slide, please. So these are some of the questions we ask about the Noachian. The channels are called valley networks. Do they indicate that Mars was warm and wet? It seems so. We have a lot of clays. They're technically known as phyllosilicates. Did these come from a warm and wet early period? And then we ask a lot of other questions about the nature of the atmosphere and the presence of polar deposits. Pedro has these slides. If you would like to have them in your school, you're welcome to them, and you can look through these in more detail. But let's go on to the next slide and look at the kinds of things that we see in the late Noachian, this earliest period of time. So shown on the right there is a poster we had for a meeting early on, and it illustrates the topography of the surface of Mars. You're looking straight down on a region of the southern highlands of Mars, and in the middle you can see a purple low area, and you can see a lot of dendritic valleys, like tree branch-shaped valleys coming into that low area. This is some of the best example for running water on the surface of early Mars. So this is very exciting. It's a different kind of climate. Next, please. We not only see a lot of dendritic patterns, and these valley networks are shown in blue on this geological map, but we see over 200 open basin lakes. What's an open basin lake? An open basin lake is a lake in which a channel flows into, it fills it up, and then flows out the other side. So we know that there was enough water to, in fact, fill the whole basin or the crater with water, as you can see in the upper right-hand diagram. The volumes of some of these are huge, okay? Something equivalent to the Caspian Sea on the Earth, or maybe Lake Baikal in Russia. This is a lot of water. So this is really significant, and if you look at the number of red dots, you can see that there are hundreds and hundreds of these open basin lakes. So not only was there water flowing across the surface, but it was forming lakes, filling them up, and having them drain as well. And this is also the time when we have the clays forming. So that's a lot of good evidence for a warm and wet early Mars. Next slide, please. And if we look at some of these, we can see really detailed evidence for what was going on. This is a picture of the Jezero crater open basin lake. It's in an area of Mars near the middle of Mars, if you will. You can see in the location map in the Isidis Basin. The upper left diagram is a perspective view. You're looking across the terrain, and that big blue depression is the lake itself. If you look at the lower left, you can see straight down and see the drainage basin where the water is accumulating and flowing through these channels into the lake. And in fact, there are deltas at the end of these channels as they open into the lake. So this is a possible landing site. Right now, it's among the highest landing sites to go to explore for the Mars 2020 mission, which will be a rover like the rover we see today, in which we will be roving across the surface of a valley depression like this to try to understand what the nature of the water flow was and to look for evidence of life. So these are incredible, and they're all over the place. So the next slide illustrates, details of the questions we were asking. And the question is then, from all this evidence, what is the nature of the climate in the ancient period of Mars history? Was it warm and wet, or could it have been something else? So the next slide illustrates a cross-section of Mars drawn from the one pole to the next. Next slide, please. And if you take a look at this, you can see on the left-hand side a polar cap, and on the right-hand side a polar cap as well. If Mars is warm and wet, then we would expect, like you see there, rainfall coming from the clouds. We would expect the water to soak into the ground and soak down into the groundwater table. So this is a view of a warm and wet early Mars. On the other hand, many of the climate models that we do don't seem to be consistent with this, and next slide please, suggest instead that Mars may in fact be cold and icy during this period of time. Not like the warm and wet Mars, but perhaps one in which it's so cold, like it is today, that it's very hard to get warm and wet conditions and to get rainfall, for example. So these are two conflicting ideas. They're very different. One is warm and wet, and the other is cold and icy. In the cold and icy model, what happens is that the atmosphere becomes more dense and a little bit more like the Earth's atmosphere. And so temperatures aren't just varying as a function of latitude, they're also varying as a function of altitude. What that means is that the water will tend to go to the high terrains and snow out. So if you look at this diagram in the bottom part of the image, any water that's in the lowlands will evaporate, go up into the atmosphere, and then snow out on the highlands and basically stay there. And so this is the cold and icy Mars. Some of my colleagues in France, François Forget at the Laboratory for Dynamic Meteorology in Paris, his interpretation is, based on these very good climate models, is that the early Mars was cold and icy, and it's very hard to get the temperatures to melt. So this is like many, many tens of degrees below 0 centigrade. So maybe minus 50 degrees or more below 0 mean annual temperatures. It's really hard to get temperatures above that. So if this is the case, next slide please, if it's a cold and icy early Mars, how can we possibly have all this evidence for running water? So this is a big mystery that we're trying to figure out right now. So tomorrow, almost our whole laboratory here at Brown will get on an airplane and head in your direction, stopping at Houston, Texas on the way, where we'll have the 47th Lunar and Planetary Science Conference. And we'll be giving papers on these topics and trying to, in fact, develop some tests and ideas about which of these two models is correct. Was Mars warm and wet, or was it cold and icy? And we know from our exploration of Antarctica that either warm and wet or cold and icy can readily support life. We see a lot of life in Antarctica. It's not life like big trees and big animals, it's microscopic life. But even in cold and icy conditions, life can exist. It's just you need to look in a different place than you would, say, when we go to the high latitudes, like above Greenland, for example, where you see life in the form of polar bears, and you better be paying attention to them because they're very hungry. So it's a very different kind of situation. And how do we actually reconcile this then? Is there a way we can have a cold and icy Mars early on and also have open basin lakes and valley networks? Well, the next slide suggests what Mars looks like in those early days according to the cold and icy model. According to that model, Mars would look like this, that above about plus 1 kilometer, it would be covered with ice, like you see in this topographic map. So that's a very different Mars than we see today. And how do we get, in fact, valley networks or open basin lakes if this is the case? Maybe this means that this model is wrong, that this model can't possibly be true because the geological evidence shows lots of evidence for alteration. It shows lots of evidence for running water and collecting water in these lakes. Well, maybe we can take this concept and figure out ways to heat the temperatures, atmospheric temperatures up sufficiently to melt the ice so that, in fact, we see evidence for running water for shorter periods of time. Maybe Mars wasn't warm and wet throughout its history of the Noachian, the earliest period, but maybe it was just only a few years or a few decades or a few hundred years at a time. So let's take this image and ask the question, next slide, please. In fact, what are the ways that we might be able to heat up the atmosphere of Mars early in its history? Well, there's several ways, actually. One of them is through greenhouse gases. If Mars was emitting methane or H2 or other greenhouse gases early on, a lot of those gases could warm Mars up. So there's a possibility that that could do the job. Secondly, we could get volcanic emissions. Volcanoes erupt, as you know from your experience in Mexico. Volcanoes are very powerful for putting debris and other things into the air, which can at least temporarily warm the atmosphere. And of course, we have the big orange thing there, which is a meteorite impact, which is in fact a projectile coming in, ejecting material and heating it up to create temporary melting that could in fact melt the ice sheet. So these are all candidates for things that might temporarily melt the ice sheet to create the valley networks. So is this the way Mars worked early on, or is it just much easier to find ways to elevate the temperature so it's always warm and wet? So the next slide shows you, in fact, the map again of where, in fact, the ice should be. So let's perform an experiment, kind of a scientific experiment. We can test this idea by superposing onto this map the distribution of the valley networks and the open basin lakes and the closed basin lakes. So in the next slide, you can see this superposition. And in fact, we see lots of evidence in the blue features there. The blue features are all the valley networks. The red dots are all the open basin lakes, and the green dots are the closed basin lakes. They're the ones the water flows in but doesn't flow out. And you can see there's a very high correlation of the open and closed basin lakes with the edge of the interpreted ice sheet shown in white. So this doesn't prove this is what's going on, but it suggests to us that this is a very good hypothesis to continue to explore. So the question is, was Mars warm and wet, rainfall, and just like it is today here on the Earth and in our environments? Or was it cold and icy, like you see in this slide here, in which the surface was covered by ice at the high altitudes, but some periods of time, impact cratering, greenhouse gases, or volcanism might have in fact created periods of time when the temperature was high enough in these areas to melt the ice to create these valley networks. So the next slide gets back to this question again. So this is the theme of which we're going to be talking about in this meeting in Houston. It's just amazing. There are going to be lots of discussions and debates, scientific debates, scientists presenting different types of evidence to test these ideas and to try to understand what's going on with life in early Mars and what is going on with the Mars climate. So we think that there is a good possibility that there was life on early Mars, and now we just need to know exactly where to go and what to do to test this. So let's go to the next slide, which takes us back to the geological column and shows, in fact, the area in the transition. We would really like to go to this area between the clays and the sulfates, between the Noachian and the Hesperian, to explore the surface to try to understand what's going on. And the good news is, next slide please, we in fact are there because Curiosity, the Mars exploration rover, for the last couple of years has been exploring just that place. Next slide please. If you take a look at this diagram here, you can see Gale Crater, the topographic map in the upper middle, and you can see the kinds of things that Mars exploration rover is studying. It is actually roving across this very transition between the late Noachian and the early Hesperian. And if you look in the upper left-hand corner, you can see lots of evidence for rounded pebbles and streams and possibly even a lake that date back to this transitional period. So spacecraft like the Mars exploration rover, they are put on the surface, and that landing site is chosen to try to help us distinguish between these hypotheses. Was Mars warm and wet, or was it cold and icy with transient melting? So this is very, very exciting because it gives us the opportunity to study these things in situ. So Ralph Millikan, a professor here at Brown, is a team member on this particular mission, and we're all eagerly analyzing the data to test ideas about whether there was life there and what the characteristics of these deposits are. So stay tuned. Keep your eye on the internet because the results of this will be coming out within the next week, some of the major findings. And also, of course, we're thinking ahead to future mission to human exploration. We just recently have been working with NASA to develop landing sites for human exploration. And this next slide, if you will, is in fact a title slide from the presentation that we made in Houston in the late fall of this past year. We have an international team that's looking at potential landing sites for humans on the surface of Mars, and it's very, very exciting. We have the Apollo 15 commander, David Scott, who is one of our team members. We have an international team of engineers and scientists, and we're looking at an area in the mid-latitudes of Mars, about the same latitude range as Washington, D.C. That's why the picture is on the left-hand side there. And we think that this will be an excellent site for future human exploration because it has buried glacial ice. We know from our remote sensing of glaciers, of the surface with radar that's orbiting the surface of Mars right now penetrates into the subsurface, that we have hundreds and hundreds of meters of nearly pure ice below a few meters of surface debris. So this is a great exploration area, and we're working in the exploration for humans to actually pick landing sites and think about the regions we would explore and how we go about doing it. NASA is proposing to send humans to Mars to establish an outpost and then a longer-term stay in the middle to late 2030s. President Obama has asked that we be in Mars space area, like in orbit and on the surface, hopefully by the end of the 2030s. Which brings me to my last point, which is this is something that cannot be done. Exploration of Mars cannot be done just by us alone. We need all of you to start thinking about Mars and really think about the kinds of things we've talked about today. Careers in science and engineering are really critically important to help us explore the solar system and to get to places like Mars. And of course, you have already taken major steps in that direction. Next slide, please. Which is, of course, with Rodolfo Vela, who is an astronaut who flew on the space shuttle, who is Mexican, and of course, he is a pathfinder in the exploration of the solar system. So we want to get you into space. We want to have you help us in this incredible endeavor, and we'd like to, in fact, engage you in careers in science and technology to really explore the solar system. Last slide, please. So please join us on our quest to explore Mars. And I want to thank Servi for setting this up, and Pedro and all my colleagues there in Mexico City for listening to us today. And we hope you find this as an exciting a journey as we do. Thank you very much.
Thank you, Jim. It's a great lecture. Please, vamos a agradecer la conferencia. It's time for the questions. Let's go start with Colegio Carol Bohr. ¿Alguna pregunta o comentario en el Colegio Carol Bohr? Si por favor activan su micrófono.
When are humans going to be able to go to Mars and make research?
So I think a simple answer to that is humans are already at Mars. You know, we have spacecraft in orbit, which are our eyes. We have rovers on the surface, which are our eyes. But it's not the same as going there yourself. So currently, NASA is talking about the mid to late 2030s. But this is not something for me to be concerned with. It's something for you to do. So it's really up to you. You know, we have the capability to go to Mars, absolutely no question. We've been to the moon. That was my first job, was working in astronaut training and mission operations for Apollo. And you know, we know how to do it. We need technology. We need people who work on this, people who are excited about it. So I would challenge you all to be the ones that move that date from 2030s to an earlier period. I think it's just in a question of whether we want to go or not. So we hope it's an international endeavor, and we hope you're all involved.
Gracias, Colegio Carol Bohr. ¿Alguna otra pregunta o comentario? Si nos activan su micrófono. ¿Está abierto el micrófono? ¿Sí? ¿Alguna otra pregunta, Colegio Carol Bohr?
We have another question. Taking into account the climate history of Mars, is there any possibility for humans to live there? Maybe not now, but later in a few years?
Mars?
Can I live there?
Yeah. Yes, I think the answer is yes. In our okay. So when we think about Antarctica, which we've been to many times, you can say that people can live there. Okay, so you need to have a life support infrastructure. That's true in Antarctica. You have to have buildings and heating to keep you from freezing, obviously, but we can do that. So it's the same on Mars in many ways. If you've seen The Martian, the movie, that's pretty close to what it would be like. Okay, so you can stay there for long periods of time if you have support, and you have to develop a way to, in place on Mars, come up with your resources. So, for example, that's one of the reasons why our landing site was so close to a glacier, which had an abundant supply of water. If our base was there, that would remove one of the biggest problems in living on Mars, which is bringing water from the Earth. It's just very inefficient to bring water from the Earth. So you would need to be able to have water, and you would need to be able to make oxygen out of the materials there. So that's the key to long-term living on Mars. I don't think it's ever going to be like Mexico City with that many people, or New York City, but I think it's going to be more like Antarctica, where there is a small group of people that's providing the infrastructure, and in our case, we have helicopters take us out to where we're doing our science. I think it's going to be very similar on Mars. You're going to have a base that's going to have maybe tens or hundreds of people, and then you're going to have scientists who are going to go out to study Mars from that direction. So yes, I think we will live on Mars eventually. I can't see far enough ahead to imagine that we would have a Mexico City on Mars, but anything's possible.
Gracias, Colegio Carol Bohr. En un momento regresamos con ustedes para más preguntas. Veo en CCH Oriente una persona lista para preguntar. ¿Hay alguna pregunta en CCH Oriente?
Sí, tenemos un par de preguntas.
Adelante.
We have a couple of questions. We have a question first by Adrian here. He's interested in knowing, in terms of measures or percentage, how much of the surface has been explored up to this moment.
Mm-hmm. That's a very good question, and the answer depends on the kind of exploration you're talking about. So we have 100% coverage of the surface of Mars at a few 100-meter resolution, maybe a few tens of meters resolution. So, for example, for a building like most of us live in, or work in, like a school building or something like that, we could see that on Mars virtually any place that it was. So we have global coverage like that. But we don't have global coverage for things like the mineralogy or extremely high resolution imaging. We have images of the surface of Mars where we could see this desk, for example, if it were on the surface of Mars. But we have probably maybe 10%. Yeah. So maybe we have perhaps 10% of the surface of Mars at that resolution. So Mars is very familiar to us in a general sense, but we also need much more data to explore to the level that really gives us the understanding.
Gracias, CCH Oriente. ¿Alguna otra pregunta o comentario?
Sí, tenemos una pregunta más. This is by Brenda. She would like to know if there is any other similar studies for other planets, if there has been research on other planets.
Yes, absolutely. Thank you. So I think we study all the planets, okay, so for sure. So we just finished a mission to Mercury, and that mission was known as Messenger. It went into orbit around Mercury, so we have a lot of coverage of Mercury. Is that the question? And so I think the key here is we have an orbiter around Venus, for example, and we have lots of them around Mars and around the Moon, and we've also visited many of the satellites. We have a spacecraft in orbit around Ceres, an asteroid. So we're studying all the planets, and we're trying to understand the basic way they work. How does a planet work? It's like if you look at an iPhone, for example, you kind of want, what's going on inside there? You like to take it apart and see what's inside. And that's what we're trying to do.
Les pido por favor a Colegio Ciudad de México si cierran su micrófono. En un momento vamos con ustedes para preguntas. ¿Alguna otra pregunta en CCH Oriente?
Yeah, we have one more question.
Correcto, adelante.
He would like to know why exactly human beings have not stepped on Marte, like on Mars. Sorry, like what are the conditions necessary for them to step on the surface of the planet?
Sure. That's a very good question. And really, if you talk to the Apollo astronauts, the astronauts that have been to the moon, they will tell you how hard it is to go to Mars. And stepping on the surface of Mars isn't as hard as getting there, because it takes a couple of years to get there. So literally, you have to carry everything with you for 2 years on the way out and a couple of years on the way back, and then what you need when you're there. And you have to survive that very, very long trip. If you have any medical conditions or difficulties, you can't just simply turn around. You have to go back and then swing around and come back. So it's really the difficult part is getting there. And we also don't understand what it does to you biologically either. There are indications from the space station and astronauts that the long duration will have an effect on you. Okay, it changes your bodily fluid because of the zero gravity. So if you're in zero gravity for 2 years, and then you land on the surface, and all of a sudden you're in 1/6 gravity or 1/3 gravity, it's going to have a major difference. So part of the big problem is figuring out how to get there. It's such a long duration.
Gracias, CCH Oriente. En un momento regresamos con ustedes para más preguntas. Voy a pasar a nuestra escuela de extensión en Canadá. Quiero verificar si en Canadá hay alguna pregunta o comentario.
Hi, I just have a question. I saw in your slide a little robot. Could you tell me about the robot? I would like to know what he is looking for and how does he works. And I know he takes pictures of the surface with the laser. Could you tell me about the robot?
Sure. So the robot that I showed was the Curiosity robot. It's about the size of a small Volkswagen, for example, or a Mini Cooper, something like that. It's actually pretty big, and it has lots of different instruments on it. It's a very sophisticated spacecraft. You can actually Google Curiosity, and it will bring it up, and you can see a lot of evidence for all the payloads, etc. But it has a great imaging system, so we can take pictures. We can look at take soil in and measure the geochemistry. We can drill into rocks and analyze the rocks. A whole host of instruments. We can actually go across the surface as a Russian instrument on board from some of our colleagues in Moscow that actually tries to sense whether there's ice below the surface or not. So it's a very, very sophisticated laboratory, and of course it's controlled from Earth, and so controlled commands are sent up for it to take a few steps and then wait and look around a few more steps and so on. So it's very it's a lot of fun to plan where to go and what to do and make the measurements, and many people, including our colleague here, Ralph Millikan, are involved in that.
Gracias.
Thank you very much.
¿Alguna otra pregunta?
Thank you. No, that's it. Thank you very much. You have another question. Wait.
Adelante.
Do you foresee that in the future the travel time may be reduced? And my second question was, you talked about the physical effect that just a travel may have or would have on the astronauts. What about the psychological effect of spending 2 years just flying in a closed compartment? Thank you.
Yes, both those questions are really good. I think the first one is that people are working on various different ion drive and other kinds of technologies that might reduce the flight time. This is not my area of expertise, but I know people are working on that. I don't think there's anything that's likely to come up in the next 5 to 10 years, but this is the thing about technology, you just don't know. And I think your second point about the psychological effects is really important. We face this in Antarctica, for example. We're only out in the field for a couple of months, but we're living in tents together, and it's very close quarters. We work together every day. We have to cook our food every day. And the psychology is critically important. We don't take people who complain a lot because, who wants to listen to that for 2 months? And the astronauts are pre-selected very much so for psychological aspects, for being compatible and understanding. The astronauts have this term which they call situational awareness. You probably recognize people who walk into a room, they have no idea anybody but themselves is in the room, and they just don't care about anybody else. That's called poor situational awareness. And you don't want to be locked up in a spacecraft for 2 years with somebody with poor situational awareness. So, people think about this a lot, and even the most compatible people, 2 years like that, it's not going to be easy. It's not going to be easy at all. And I think in addition to the medical aspects, the psychological ones are very, very large. And, this is a lot of studies of the space station astronauts are going on now to look at these kinds of compatibility factors, how much room you need to not feel like, you're, and how to work out any disputes that come up, that are bound to come up in terms of this kind of voyage. Very good question.
Gracias, UNAM Canadá. Voy a pasar a Colegio Ciudad de México. Quiero verificar si en Colegio Ciudad de México hay alguna pregunta o comentario. Si activan su micrófono en Ciudad de México.
My question is that out of the two hypotheses that you mentioned, cold and icy and warm and wet, which one do you support and why?
That's a very good question. So I'm actually a co-author. That means I helped in part of the cold and icy studies. I see them as two different in members, the warm and wet on the one hand and the cold and icy on the other. And I think that we need to test these two as in members to see what the truth is. And I think that, the cold and icy, if you think about this as the cold and icy, okay, if you have a huge volcanic eruption, it's moving to warm and wet a little bit, and then it moves back to cold and icy. So I suspect that the difference is somewhere in between, but it's not just an average. It means that there's one of the two is going on, and then there's some factor that's creating the difference. So my own personal view is that based on my understanding of the early climate of Mars, it is really hard to get the temperatures above the level at which you get consistent warm and wet conditions with rainfall. It's just really hard to do. So I would say at the present time, I'm exploring in more detail the cold and icy hypothesis to see if we can actually make it consistent with all these other observations about valley networks and open basin lakes. So I would say I tentatively favor that one now, and we're trying to work out whether it can actually do the job of explaining what's going on by having these periodic periods of warming.
Gracias, Colegio Ciudad de México. ¿Alguna otra pregunta o comentario?
Yeah. I was wondering if you can use like nuclear energy in Mars, because I don't remember exact year. I think it was after the Cold War. A treaty was signed that you cannot put, like, I don't know if it's nuclear material or nuclear weapons in space. So you can use like nuclear energy on Mars. Could you take a nuclear reactor or enough plutonium to produce energy over Mars?
Sure. So I think that using nuclear energy is almost an absolute necessity when you go to Mars. So of course you're way far away from the sun, and so many of the spacecraft, if they have solar panels, there's not enough sunlight out there to actually make them work efficiently. So I think a nuclear power station, a small one, is, I think, probably absolutely essential for the exploration of Mars on the surface. And in fact, we do have small nuclear power plants. It's not like something huge. It's just a small container that contains radioactive material that can be used to generate heat and electricity. We flew those on virtually all the Apollo missions to the moon. So it's not dangerous in the sense that it's not a big reactor like Fukushima or something like that. It's a small contain a pellet of radioactive material that in fact can generate the energy. So all the scientific experiments on the surface of the moon, for example, that were left on the surface of the moon were powered by what's called an RTG, a radioisotopic thermoelectric generator, which is a fancy name for a very, very small nuclear power plant. So I think we've shown that it can be done, we've shown that it can be done safely, and I think it is essential for the exploration of Mars.
Gracias, gracias Colegio Ciudad de México. En un momento regresamos con ustedes para más preguntas. Voy a pasar a Preparatoria 9. Quiero ver si en Prepa 9 hay alguna pregunta o comentario. Si por favor activan su micrófono.
Okay, you can hear me?
Yes.
Yes.
Okay, my question, Professor Jim, are the next. Do you think that the disappearance of water of Mars is due to any change in solar radiation received by the planet or some other event in the period of rotation and draft angle?
The last part? Did you get the last part? Can you repeat the last part?
Or some other event in the period of rotation and draft of the angle of the planet.
Right. Okay, I got it. So, yeah. So yeah, you're right. You get heat from the interior, and you get heat from the sun, and the heat from the sun can vary as a function of orientation of the planet. I think today Mars has cooled down a lot because it's 4.5 billion years old. So that means that there's not a lot of heat coming out from the interior. But earlier in its history, there was a lot more heat coming out, and part of the melting that we see could be due to heat coming out of the interior and melting at the base of this ice deposits. But also, as you point out, I think there's lots of possibilities for variations in the eccentricity as well as variation in the rotation axis for changing the incident solar radiation, the amount of sunlight coming in, and creating melting. So I think that's another really good possibility. And we haven't sorted those out yet, so it's a very good area of research and a very good question. Thank you.
Gracias, Prepa 9. ¿Alguna otra pregunta o comentario?
Yes, we have another question. The question is, can we make a kind of model of Mars to know how could interact or react the life from Earth in Mars? I mean, I think it's a risk take life from Mars, isn't?
Did you get that? No. I'm sorry, I didn't understand the question. Maybe hold the mic a little further away.
Can we make a model of Mars to know how interacts the life from Earth in Mars?
I see. So you're saying, can we make a model of Mars on the Earth and see if it would support life?
Yes.
Okay. Yeah, in fact, many people are trying to do that. So we have experimental chambers that, in fact, try to get the conditions very similar to what we see on Mars. And then we develop these kind of like put in some different chemicals and the temperature gradients, etc. And that really is a way to test that. So it's very clear that under conditions that we see on Mars, life could in fact exist. And we see this in Antarctica. We see Mars-like conditions, and we also see microscopic life, algae, and other kinds of features. So it's an area, it's kind of called astrobiology. That is a study of the biology elsewhere in the solar system. And experiments like you describe are definitely part of that.
Gracias, Prepa 9. En un momento regresamos con ustedes para más preguntas. Aquí en Universum, here at Universum, the next question.
About the proofs of curiosity, is there any evidence of this climate in which theory is identified with these proofs of is warm and weather or ice and cold?
Right. So the key thing here is that come in, grab a seat here. So the key thing here is that people who are geologists, okay, people who are geologists think very much that when you see these channels that are extending across the surface, and you see these open basin lakes where the water used to be, that's just really good evidence for rainfall, because that's the way we see it on the Earth. And that's a logical conclusion. On the other hand, Mars may not act exactly like the Earth. And so when we take a look at these types of features and we say, well, could they be formed elsewhere? For example, very few people have been to Antarctica, and so when we go there, we see similar types of features. We actually see stream channels, but they only form for a few weeks of the year when it's the warmest, and typically below that they freeze and they go away. Literally the water sublimates away, so the rivers are empty. But for a few weeks a year, the temperatures are high enough so that some of the ice melts and flows across the surface. So I think the answer to your question is that there's good evidence for both ideas, both end members, warm and wet and cold and icy. But the problem is that we all don't have the same experience, and so we have to go to Antarctica to try to see how that process works, see if we can map it to Mars, and then we have to work on the climate models to see if the climate, through maybe massive greenhouse gases or something, could warm up sufficiently for it to rain. We can also look, as we're doing here at Brown, at the characteristics of the patterns of runoff. Okay, what do these channels look like? One of my students, Kat Scanlon, she just defended her PhD thesis last Friday, and she did experiments on doing rainfall in these climate models and also snowmelt, and then compared the patterns of those two to see how similar they were to the patterns of the valley networks. So there's a lot of tests like that go on, but it's a lot of it depends on your experience. For example, growing up in Mexico City, you would have a very different view of the climate than I would growing up in Providence, Rhode Island, where it's typically much colder throughout the year. So I think those are the kind of perspectives, and it's really important as a scientist to travel and learn these different environments and these different perspectives. Thanks.
Thank you, Dr. Jim. Here are another question.
Okay. We have seen similar rocks between Mars and the Antarctic. Have you been studied the composition of these rocks, or are similar only about the structure?
Yes, so we do study the composition of the rocks, and the composition is very important because different rocks of different rock types weather in different ways, and so it's really amazing to see this. So we bring these rocks back to Earth. We have lots of them here at Brown. I should have brought one up to show you, but the types of weathering you see on them are just amazing, amazingly different. And so, for example, a sandstone will weather very differently than a basalt rock. And typically we can look at those and look at the differences, and also the way the weathering rinds, so the skin on the rock as it's weathering away is very different in the different environments. So we can do that on the Earth, and we can actually do it on Mars as well with these drills and other features on the Curiosity rover. So it's a very good question. The mineralogy and the composition of the rocks is critically important, and we learn a lot about that. So thank you.
Thank you, Dr. Jim. Here are another question.
I have two questions. The first one, which are the countries that are being involved in the project of the Mars exploration? And the second one, is there any other project that is being developed at the same time in other countries like Russia or Japan?
Yes. So your first question was about different articles or spacecraft, or?
No, I mean, which are the countries that are being involved in this project?
So, there are lots of different things being developed at the present time, and they're developed internationally. So this past Monday, that would be just a few days ago, the Russians launched a European spacecraft which had international experiments on board to go to Mars. So it's an incredibly international endeavor. So that spacecraft was part of the ExoMars program, and it's called a trace gas orbiter. And it's on its way to Mars right now, launched on a Russian rocket with European experiments and some American participation, very international program. And so what was that studying? It's trying to understand whether some of these greenhouse gases that might have heated up early Mars might exist in trace amounts in the present atmosphere of Mars. So that's trace gas orbiter. So we were looking for traces of these gases that can give us clues as to what the greenhouse gases were even today and might have been even more abundant. So, I like your arrow shirt. We really want to have you be the person who designs the spacecraft and makes the experiments that we will be flying to Mars in the future. And then you can also apply to the astronaut corps to be in line to go yourself.
Thank you, Dr. Jim. Could we have another round of questions? Is it okay for you?
Sure. Sorry.
Ok, entonces vamos a otra ronda de preguntas con las sedes remotas. Voy a regresar con Colegio Carol Bor para verificar si hay alguna pregunta final en su sede. Colegio Carol Bor.
Thank you.
Adelante.
Thank you. There are no more questions.
Adelante. No. Correcto, gracias, Colegio Carol Bor. Voy a CCH Oriente. Quiero verificar si hay alguna última pregunta en CCH Oriente.
Yeah, we have a question.
Correcto. Estamos teniendo pequeños problemas con su audio en este momento. ¿Podrían hacer la pregunta pausada, por favor?
Sí, la pregunta. The kind of water that has been found, or the evidence of water that has been found in Mars, could be possibly consumed by human beings, and if so, is there any? I don't know. Are you trying maybe do the conditions of the atmosphere in the planet Earth? Is it possible that all of this research leads us to take our life as we know it on the Earth to Mars? Could human beings live on Mars in a near or far future? And that's
Okay, so the nature of the water on Mars, in principle, the water should be very similar to what we see here on the Earth in its purest form, for sure. But the question is, how pure is the water? And we know, for example, that if water is mixing with rocks and doesn't get rinsed out, so to speak, that you will get very, very salty water built up. And so my suspicion is that the water that we see flowing on the surface of Mars right now, there's these features called slope lineae that look to be water flowing down the surface, that this would be very, very, very salty water, like a brine. And in Antarctica we see the same thing. The water in the little lakes is extremely salty. It's some of the saltiest water that we see on the Earth. And so that's a problem in the sense you would have to distill the water and get rid of all the salts to make it so that you could drink it on Mars. On the other hand, we see lots of evidence for these icy glaciers deposits where the ice should be much more pure, and I suspect that if you melted that, you could drink it pretty safely and it would be fine. On the other hand, the question of can we make Mars more like the Earth? Some people say that we should terraform Earth. We should make the Mars environment like the Earth's environment by changing the atmosphere in some way or another, radically changing the atmosphere. We don't really know how to do that, and even if we did know how to do that, I would personally find it probably not the best thing to do, because if we look at what we're doing to our environment here on the Earth with our changes like global warming and all these other types of modifications, it's not very well understood how that works. So if we try to perform a complete experiment of changing Mars' climate to make it more Earth-like, first of all, we would destroy a scientific laboratory that exists on Mars. And the second thing is that I think it's an experiment that I wouldn't want to perform because I don't know the outcome, and I fear that it could mess it up much more than it could make it more Earth-like. So that's left for future generations to decide, but I'm very skeptical about why we should do that and whether we should. When we go to Antarctica, we have to try to do no changes at all. The credo in Antarctica is leave no footprints. Let's see, make no changes, leave only footprints, and try not to leave those. So we don't want to change the environment because it's a very, very interesting thing to study.
Gracias, CCH Oriente. Voy a Colegio Ciudad de México. Quiero verificar si en Colegio Ciudad de México hay alguna última pregunta o comentario.
Good morning. I have two questions. The first one, based on your geological studies, do you have an idea of how water was formed in Mars? And second, you told us that you want to send humans to Mars. So how are you going to do something like Biosphere 2 or something like that?
Yeah, I didn't catch the first one, but I did hear the second one. And Pedro, maybe you could translate the first one for. I mean, not translate, but repeat the first one for me.
Let me check. ¿Podrían repetir la primera pregunta, por favor?
Well, based on your geological studies, do you have an idea of how water was formed in Mars?
What?
Tenemos un pequeño problema con su audio. Si pudieran volver a repetir un poquito más pausado, por favor.
Okay. So, okay. I think I can answer that. So, I'm sorry. It's not the. It's just the break. It breaks up. But anyway, so I think you. First of all, let's start with Biosphere 2. So that's exactly like the kind of thing we would be thinking about building on Mars. Okay. One of my friends, Mark Nelson, was in Biosphere 2 for 2 years, and we've actually been having a great conversation. He's on our team for the Mars landing sites, and when I talked to him and I said, hey Mark, you of all people, you should be able to tell us what it's like being in a biosphere, which we would build on Mars. And I said, would you join our team? And he said, absolutely, Jim, but I would like to bring one person with me. I said, sure. And he said, who is it? He said, the person who built Biosphere 2. So we have a great team because we have not only the person who built Biosphere 2 to think about how we would build that on Mars, but also we would be able to have someone who has been there for 2 years in a biosphere and give us good advice on the psychology, the modes of life and so on. It was really interesting I was very lucky to have Mark, and he invited me to come to his party when he came out of Biosphere 2. So Mark and his 6 colleagues came out about 11 in the morning, I think, as I remember, and it was just great to see them and sit around a table and have the first meal outside of the Biosphere after they exited after 2 years. And it was interesting because, some people say, oh, you really want to go down to McDonald's and get a really Big Mac or something like that. And he said, I know where every bit of my food has come from in the last 2 years. And I grew it all, I've made it all, I cooked it all, and I don't want to eat anything I don't know where it came from. So that was an interesting experience. He was quite proud of the fact that he really knew what he was eating because he had done it all himself. And that's the kind of psychology you're going to have on Mars. And remember when Matt Damon, the actor, was on Mars in The Martian, he had that same experience, okay? He had to figure out what to grow, and you could see him figuring out what to do with all the potatoes and what to do when the potatoes went wrong, etc. So Biosphere 2 is a good metaphor. And I think in terms of the power, if that was your question about the location of the power, you can get some solar energy, but mostly it's going to come from essentially small nuclear power sources, like we talked about that the Apollo astronauts took to the moon.
Thank you, Dr. Jim. The final question here at Universum Museum.
Hi, I promise it's the last. Do you consider that the Mars exploration is priority for the NASA? If it is not the case, what is the most important investigation program that you are working for?
Sure. So certainly for human exploration of Mars, that's the most important program for NASA as an agency. President Obama has said that he wants the United States and our international colleagues to be in the vicinity of Mars, in orbit and on the surface by the late 2030s. So NASA is building towards that. But exploration is not just with humans, and it's not just to actually put flags and footprints on the surface. It's to really do scientific exploration to understand what's going on. So that's why the actual legislation that created NASA said that it needed to explore the cosmos, okay, not just the moon, not just Mars, not just our solar system, other solar systems, interplanetary space, and so on. So NASA has a very, very robust exploration program for other missions to other planets. I just mentioned the one to Messenger to Mercury. We had Magellan to Venus. We have a couple of spacecraft, several spacecraft in orbit and on the surface of Mars. We have one going into orbit around Jupiter. And we have spacecraft that are designed to visit the outer planet satellites. We have them in orbit around Saturn. It just flew by Pluto and is going to come up to another object in a few years. So there's a huge, broad exploration program of this solar system and also of other stars and other planetary bodies around other solar systems. The James Webb Telescope is going to be launched in a couple of years, and that will provide a revolutionary view of other solar systems. And this is a critical aspect of, in fact, our perception of the Earth. Many of you know that when you grow up and you visit places outside of Mexico City, maybe another country, another part of the world, it really changes your perspective on understanding what's going on. And that's the way we look at the planets, too. So we've been exploring for the last 50 years with NASA all these different planetary bodies. It's completely changed our view of what the Earth is and its place in the solar system. And now we're on the verge of this incredible journey to these other stars and also to investigating what solar systems look like around other stars. And I think it's just absolutely sure that we will, in fact, find life elsewhere, if not in this solar system, certainly in other solar systems. So it's an exciting time ahead, and we need all the help we can get from you all to help us get there. Science and engineering, poetry, art, all of these things contribute to this effort, and I hope you'll join us in this endeavor. Thank you.
Thanks a lot, Dr. Jim. We want to thank your participation with an applause.
Thank you very much. It was my pleasure, and they were great questions, really good questions. Keep it up.
Gracias. Thank you. I don't see Brian. If Brian is over there, I don't see Brian. Maybe he went out. But thanks a lot for your help. Thanks a lot for SSRB collaboration. Thanks a lot, Brian. Thanks a lot, Ricky. That's all. See you in the next video conference.
Okay, sounds great. I'd be happy to do it again sometime soon.
Thanks a lot.
Okay. Hasta luego.